Welcome to this course on Illumination Engineering and Electric Utility Services. This course presupposes a basic understanding of basic electrical engineering and electrical circuits. This is the lecture 1 of the course dealing with introduction, and to begin with, let us look at the instructional objectives for this particular lesson. What do we expect at the end of this lesson? Number 1, state the need for illumination. Number 2, define good illumination. 3, state what comprises an electric utility. 4, list standard voltage levels. 5, understand need for high voltages for transmission. So, these are the major instructional objectives, and at the end of the course one must be able to understand these instructional objectives. The course overview is as follows. The course overview begins with the radiation and color, the eye and vision, obviously because most of our illumination is sensed through our eyes. There is a chapter on eye and vision, followed by different entities of a illuminating system. There are various components that form an illumination system. Therefore, one looks at the entities that comprise an illumination system. The light sources have to be observed considering the daylight, which is the normal natural light, the artificial lights formed by incandescent, electric discharge, fluorescent, arc lamps and lasers. The luminaires, wiring, switching and control circuits. Obviously, here there is a implied understanding that it is the artificial lighting employs electrical energy, and hence the various control aspects that involve using electrical circuit systems is being addressed. Laws of illumination, illumination from point, line and surface sources. Continuing with the overview of the course, then comes the need for measurement. Let us recall what Lord Kelvin said: unless we measure whatever we try to understand or analyze a study, it is incomplete. Therefore, there is a need to measure, and hence the topic of photometry, spectrophotometry, photocells, etc. is the next. Continuing with the course overview, you can see the effect of the environment, and all of us have encountered glare at some point or the other. How the glare arises, how it is specified, how it is avoided, these are some of the issues. Having talked about all the principles, one looks at the general illuminating design. Then the illumination for interior purposes, could it be residential, office, departmental stores, industrial environment, an indoor stadium, theatre or hospital. Then comes the exterior lighting, which commonly we encounter as flood lighting, street lighting, aviation lighting, transport lighting, lighting for displays and signaling, neon signs, LED, LCD displays, beacons and lighting for surveillance. As one could see, lighting is for functionality, lighting is for surveillance or security aspects. And all this, as already told, involves electrical systems. So, electrical utility services for various large buildings, office complexes and layout of different metering instruments and protection units are necessary next. So, and once we have this, we need to look at the various types of loads and how they are individually protected or in a group, and one must emphasize that all this needs some kind of a conductors to carry the electrical energy, which are in the form of cables or wires, and the moment we use cables, there are insulating materials involved, and there are certain potential sources for fire and necessary precautions. And these days of advanced technologies, one needs a continuous power supply. Therefore, there are necessities for having an emergency supply and a standby mode, and one of the common techniques that is used these days is to use uninterrupted power supply. In fact, the computer control of this lecture is also being helped in the form of by use of a UPS. A specific design problem would be addressed towards the end. All this assumes that one has all basic understanding of basic electrical engineering principles and ability to analyze a electrical system in the form of a basic electrical circuit. Let us see. This picture here shows the various streams of sciences and various professions and how they are made useful to humanity or serve the society or humanity. Let us take the first profession, the medicine, which is helping us to live a healthy life, is basically involved in the application of sciences of physiology and psychology to address the usefulness to humanity, which is somewhat empathic in nature. Coming to architecture, it needs economics together with art to be able to provide proper ability of architectural facilities for human this support. Now, illumination engineering is one such profession which involves physiological aspects as well as psychological aspects, because the functionality of illumination system depends on the environment, and most of the use of light is in perceiving objects through our eyes. Therefore, psychology and physiology play a lot of role. But at the same time, like any engineering science, it needs all the inputs of exact sciences of mathematics, chemistry, physics and economics, because optimized usage of resources has to be maintained to be able to get the illumination. All this not compromising on aesthetics. So, illumination engineering brings in a set of new professionals who are needed to have much more broader areas of sciences and art rather than any other profession like medicine or architecture. So, it is very clear that the humans depend very much on light, and it is said that light is that natural phenomena which is very vital for our existence, is taken for granted. It's never, I mean, we assume that it is available. We never even know what would have been the life if the light was not there. In fact, if you recall, our life involves in the cyclic variation of day and night with sunrise and sunset. Prehistoric man had all activities restricted only to the sunrise to sunset. And today, in fact, we have more or less extended activity period, and we talk of systems which are operational round the clock, round the year, in terms of 365 24/7 services. All this is possible because of extended activity period due to the artificial light, and artificial light has to be planned, optimized, at the same time minimizing the utilization of the available resources. This is a very important aspect, minimizing. Now, this artificial illumination could be to be borne in mind that vision is affected by this artificial illumination and is the most important sense among the various senses which human beings have, and is this one sense through which we acquire more than 80% of our information. That is to be kept in mind. The acquisition of information could be through sun or moon. Moonlight is basically direct or reflected. Artificial light, whenever created, has to be closest to natural light, that is closest to the sunlight, which is the most important source of daylight or natural light. Here it must be necessary for us to see what is a good lighting? In fact, this has been one of our first instructional objectives. We say the lighting is good when our eyes can clearly and pleasantly perceive the things around us. This is what Teichmuller says, and that is to be kept in mind. So, artificial light therefore has to be functional. It should be pleasing to physiologically as well as suit psychologically to the mood. For instance, the type of lighting that is required when I am praying or meditating is different from the type of light I need when I am doing a precision soldering on a PCB. That has to be kept in mind. So, it could be using a large number of sources. That is why I have written here multiple sources, and sources should be economic. Already we said illumination engineer has to have an idea of exact sciences of maths, physics, chemistry together with understanding of physiology and psychology of humans, at the same time keeping in mind economics, and produce an aesthetic artificial lighting system. So, the sources have to be economic, energy efficient. All sources today employ electrical energy in some form or the other. Therefore, one needs to look at how electrical energy is supplied. As already learnt in a basic courses, it could be in the form of a alternating current, that is, which cycles at a particular frequency, which is commonly at 50 Hz in our country and most parts of the Europe, and few parts in North America is at 60 Hz, or direct current. Usually as I said, it is AC and it is either single phase or three phase. We will look into the details, but one has to recall that any current flow calls for a closed circuit. Without a closed circuit, current cannot flow. This has to be kept in mind. And the other issue which one has to remember is that there are certain losses in all electrical circuits or lines. Remember that every conductor has a certain resistance to flow of current, which is expressed as resistance, and any current carrying conductor has a associated magnetic field. Therefore, it has a certain inductance associated with it, and any conductor raised at a certain potential separated from another conductor separated by a dielectric medium possesses a capacitance. So, in that sense, every element of an electrical circuit has all the three components, and it is this resistive part of the network that gives rise to losses. And our aim in having an electrical system must be to reduce these losses. And the losses, as may be recalled from the courses in electrical engineering, is that are given by I squared R, where I is the line current flowing through the line connecting your energy supply and the illumination system. We are looking at the illumination systems in this particular program, and at this point of time we are looking at the fact that artificial light sources use electrical energy. We are trying to see how these electrical energy systems work, and R stands for the line resistance. Longer the line, higher the resistance. So, what do we do? In order to reduce, we find, keeping in mind, for a particular power level, current increases with increase in voltage. Bearing in mind, look at the equation P equal to V into I. One could reduce the current if we increase the voltage. Hence, losses are minimized by supplying at higher voltages. So, invariably power transmission is at higher voltages. However, energy is obtained either in the form of a hydro or thermal. Thermal does include coal based nuclear energy also, and being hydro or thermal, being a coal based or a nuclear, you understand coal based stations are located at the pit head of a coal mine, hydro stations are located at the hydro reservoirs, and nuclear stations for purpose of safety are located away. As a result, power stations are very far from load centers. Therefore, power has to be transmitted at high voltages to reduce the losses, and This may be mentioned at this point of time. Standard levels for transmission are 132, 220, 340, 400, 735, 765, 1000 kV AC. Now all these are kilovolts, and it must be mentioned at this point of time the highest system voltage as of today in the country is 400 kV, and 800 kilovolt class, that is 735 kV and 765 kV, is perhaps the next higher level which the country is thinking of. That must be borne in mind. Electric current sources DC or AC, it is, in fact, we are trying to recall what has been done about the electrical current sources. They are either from hydro or thermal, and the picture here depicts the complete power system. One could see a generator which could be generating at a 11 kV or a 33 kV, which is stepped up, and a transmission line maybe at 132, 220 or 400 kV transmits, which is stepped down for a distribution line which could be distributing at 66, 33 or 11 kV, and which is further stepped down and through a substation supplies the loads at 400 volts. We will look into what this connotes. So what do we see? We see that there is a generator, there is a transmission system, there is a distribution system, and there are transformers which enable stepping up, stepping down, and in the voltages. And here I have not put anything beyond 400 kV because today the system voltage is, highest system voltage available in the country is 400 kV. Load in a practical system is unbalanced. We look at how it is balanced or unbalanced, what it means. We have already done in basic courses, but let us see what it is. Now, before we go further on any of these things, what 400 volts 3 phase 50 Hz means to us. 400 volts 3 phase 50 Hz tells us that the supply is 3 phase AC at a frequency of 50 Hz with a line to line voltage of 400 volts RMS. As can be seen from this figure, it is a periodic signal of 20 milliseconds, that is 50 Hz. 1 over 20 milliseconds gives us 50 Hz, and it has a peak magnitude of 564 volts. Now, as may be observed, this is a sinusoidal voltage. This is a line to line voltage. It will become clear what a line to line voltage is when we look at the 3 phase connections. A little later, we will be looking into the generation aspect of a single phase AC generation, which shows to us that the generation by nature is sinusoidal, and the easy way of expressing the complete sinusoidal voltage is in terms of what we call as phases or RMS values, and it is known that for a sinusoidal waveform the peak to RMS ratio is root 2. Therefore, we have 400 root 2 as 564. The another important thing why we talk of RMS is we are trying to have equivalence between DC and AC in terms of heating, and RMS value gives us an equivalent AC value that can produce the same heat. Now, let us consider the single phase AC generation. In order to consider a single phase AC generation, recall that when a magnetic current carrying conductor is moved in a magnetic field, it produces induced EMF, and this is explained through a figure. We will consider here a loop AB carried by a spindle and rotated anticlockwise. You can see here there is a loop AB which is being moved by a spindle, and in the field of a permanent magnet north south at a constant velocity in an anticlockwise fashion. And you can see that there are coil ends which are brought out, these through the slip rings. They are insulated, okay, and two carbon brushes E1 E2 are where the EMF is collected and is connected to the load. So this is how, now when the plane of the coil is horizontal, there is no EMF, and sides A and B do not cut any flux, and this becomes so If we have the v, the velocity of each side given in meters per second, the AL represents velocity. Let us see this. You see, this is the vertical hatch lines are the flow of magnetic field, and this is the loop AB which is being moved anti-clockwise. The AL shows the peripheral velocity of this coil. As can be seen, since this velocity is radially outwards along the anti-clockwise direction, it has a component in the horizontal as well as vertical, and it is the perpendicular component which is responsible for the generation of EMF, and therefore we will see that how one gets the voltage generated. Now, this is a situation when we consider that the coil has been rotated through an angle theta from the horizontal, and as already said, AL is resolved into AM, AN, okay, and we can write AM is the perpendicular component which is V sin theta and V cos theta, and we have already said, this is from the Faraday's law of electromagnetic induction, that EMF is generated in A only due to AM, because only that component produces a perpendicular this thing between the flux density and the direction. Now, here one could say, if B be the magnetic flux density, L be the length of the sides A and B, then we know that EMF generated on one side would be BLV sin theta. V sin theta is the velocity component, L is the length of the conductor involved, B is the magnetic flux density. This is the voltage generated due to the flux cut by one side of the coil. Remember that the coil has two sides, therefore you have total EMF generated is equal to 2BLV sin theta. Let us look at the figure once again. What do we have? We have a permanent magnet which is shown by two poles, north and south, in which there is a conducting loop AB which is being rotated with the help of a spindle about the axis DD in anticlockwise direction at a constant velocity. There are two slip rings C1 and C2 and carbon brushes E1 and E2. Through carbon brushes E1, E2, generated EMF is picked and connected to the load R. So, the total EMF generated is 2BLV sin theta, and if theta is 90 degrees, the coil is vertical and the EMF generated is a maximum, and therefore EM or the E maximum is 2BLV. Hence, one arrives at the equation as E is equal to EM sin theta. Let us take a look at the velocity component once again. The hatch lines show the flux lines due to the north-south magnetic field, and AB is the coil loop which is being rotated, and at a particular point theta away from the horizontal, we find the velocity is directed towards AL, which can be resolved into perpendicular and horizontal components in terms of AM and AN. AM is perpendicular to the flux density. Remember that when we are talking about the perpendicular nature of the velocity component, it is perpendicular to the magnetic field. That is what we are looking at, not perpendicular to the x-axis. It as understood, as normally understood. So, total EMF we have already seen that E is going to be 2BLV sin theta, a maxima is 2BLV, hence we have E as EM sin theta. So, this shows that a single phase generated EMF is sinusoidal in nature with a certain peak, and if the B is the breadth of the loop, N is the speed of rotation, then one could say V is the velocity equal to pi b n meters per second. Hence, E max becomes 2 pi b b a n v or 2 pi b a n, where A is the loop area in square units. And if there be n turns, or remember, if the loop is replaced by a coil of n turns, which is normally the case in a generator, you have Em as 2 pi BANN. That being the case, one arrives at the equation as Em sin theta. So, this tells us that the voltage generated is sinusoidal in nature with a magnitude of Em. Okay, this is the essence of a single phase generation. Now, what is a three phase generation? Let us see. Consider that there are three coils, just as we had a single loop rotated anticlockwise in the previous situation. Let us say we have three coils which are placed on a single axis at 120 degrees from each other, as shown in this figure. You have RR1 forming one loop, BB1 forming a second loop, YY1 forming a third loop, with all these axes at 120 degrees to each other. That is how you have three coils, and let us say, just as we did in case of a single loop in the previous single phase generation, we rotate anticlockwise at a constant speed in a magnetic field due to north-south magnetic poles. We will see what is the nature of the EMF generated. Mind you, these are three similar loops and they are fixed at 120 degrees to one another. Now, here one may say the notation RR1, YY1 and BB1 has been used because it is often helps the people on the field to have a color code in the form of a red, yellow, blue. That is what has been done. Now, just as we did in the previous case, they are connected to the slip rings on the shaft. Then you have, there are finish and start terminals. Here the notation used is RYB are finish terminals, R1, Y1, B1 are start terminals, and they are rotated anticlockwise at uniform speed in the magnetic field. Now, we already know that supposing there is a particular loop rotated in a magnetic field anticlockwise, we find that the generated EMF is sinusoidal. Now, what we are going to show in this particular case is when there are three loops, it will be as though there are three voltages generated at each displaced in time, which is equivalent to displacement of 120 degrees phase shift or electrical shift. Now, recall this figure where it shows, this is all the figure 1, the way it is placed, the RR1 is not cutting any flux, therefore, the voltage generated in RR1 is 0. As you recall, the velocity component has to be perpendicular to the magnetic flux, only then there is a induced EMF. Okay. So, that being the case, EMF in RR1 is 0. Let us see how one could. Now, let us move the RR1 by 90 degrees, then you have EMF is in RR1 a maximum, and one could see this in figure 2. This is the situation where RR1 has moved and you find that it is cutting the maximum flux, the velocity vector is going to cut the maximum, you have the maximum EMF generated. Now, as there are three coils or three loops fixed at 120 degrees to one another, you will find that there is a time or a time lag equivalent to 120 degrees about this rotation in attaining a maximum. Like theta equal to 90, you got a maximum for RR1, you will have a maximum for YY1 at 210 degrees, 90 plus 120, and at 330 for the BB1. That is, you have, just as you had a 120 degrees physical phase shift between the three coils, you will have an electrical shift or shift in generated EMF maxima. So, the waveform therefore generated could be like this. As you can see, you have EMF in RR1 shown by a bold line followed by a dotted line for EMF in BB1 and hash line for EMF in YY1. As you can see, there is a time difference between each of these in reaching their peak and the 0. As you can see, RR1 is reaching begins at a 0 and reaches the first 0 at the end of the half cycle at 180 degrees electrical, which is proportionate to your 10 milliseconds in a 50 Hz. And what do we find? The first 0 beginning from negative going positive for YY1 is at 120 degrees away from the beginning, which is corresponding to 120 by 180 into 10, that is 6 by 9, 2/3 of 10, that is 6.67 milliseconds later, that is 120 degrees later, YY1 comes. There is a phase shift, and BB1 likewise comes 240 degrees away from the RR1. So that's how we see that a three-phase waveform is generated. Since the three coils are identical in size and shape, and they generate same amplitude but lag 120 degrees and 240 degrees respectively, which in the form of expressions is expressed as ER equal to EM sin theta, EY equal to EM sin theta minus 120, EB is equal to EM sin theta minus 240. So what have we seen? We have seen that AC generation is sinusoidal, and it is possible to generate three-phase source in a single generator by having identical coils placed 120 degrees apart from each other, and that's been done, and we find that generates. Now once you have a three-phase generation, now the question arises, how do we use this? This is used by various connections. These connections are two major methods which are adapted are delta and star. So three-phase connections could be a delta. As you can see, three sources are connected, because if we take the instantaneous sum of the voltages generated when connected, it is a 0, and therefore the moment you do this, we have two things coming up. There are lines and phases. So you have line quantities and phase quantities coming into picture. Within the delta, the currents and the voltage currents through and voltages across are called phase quantities, and the three lines employed, the currents through them are called line currents, and the voltage across them are called line voltages. As may be seen, the line voltages are equal to phase voltages in case of a delta, and as I told you, there are line quantities which are IR, IY, IB, VRY, VYB, VBR, and phase quantities are IRY, IYB, IBR, VRY, VYB, VBR. So what do we have? In case of a delta, we have line voltages equal to phase voltages. Now here it may be coming to somebody's mind, why we are talking about line and phase, why delta? Had we connected these three sources to three different loads in a separate manner, we would have used 6 set of lines, 2 lines for each voltage source. That way we use 6 conductors. As against that, when we make a connection in the form of a delta or a star, we reduce the number of lines employed and thereby optimize the amount of copper that is used in transmitting this power, and this is the usefulness. Now The other connection, as I told you, apart from delta, it could be a star. The star connection is shown here, and the junction point is what we call as the star point. Now, remember the three sources we had in a three-phase generation. Say I connect all the three starts or all the three finishes together, then I would find that there is no harm and I can use just three lines, and if I have identical loads and they draw identical currents, then I can see that instead of 6 conductors I could have perhaps done with 4, but since the fourth conductor, which forms the neutral conductor, carries 0 instantaneous current, sum of the 0, it need not be there. Once again, instead of having 6, we are able to do with 3 lines, and therefore, and one could easily observe the phase currents are equal to line currents, whereas the phase voltages are not equal to line voltages. Phase voltages are obviously less than the line voltages. Needless for me to mention at this point that these are analyzed using the complex algebra, because each of these quantities in AC has both magnitude and phase. So we have phase quantities as IR, IY, IB, and the phase voltages as VRS, VYS, VBS, and line quantities as IR, IY, IB, VRY, VYB, VBR become the line quantities. Now you remember we said it is 440 volts line to line. So that is the thing. Between this line R and Y, the voltage is going to be 400 volts or 440 volts. When you say it is line voltage, it is that. So they could be in delta or star. Now comes the question of loads. Now we talk of term loads may be balanced. You recall when we showed the diagram of the power system, we said generally loads are three-phase unbalanced. What do we mean by balanced? We have already said load has nature in the form of a resistance, inductance and capacitance, all electrical circuits. So the combination is talked in terms of resistance and reactance. Reactance could be due to inductance or capacitance. Now in a three-phase connection where we said it could be delta or a star, if the load impedance is same both in magnitude and phase in all the three phases, then I say it is balanced load. When I mean magnitude and phase, it means both the reactive component and the reactive component and the resistive components are same. If I define that the R is the resistance in a phase, it is same in all the three phases. If I say X is the reactance of a phase, it is same in all the three phases. That is when we say that it is a balanced load. So loads could be balanced. A balanced load means impedance nature same in all three phases, that is equal in both magnitude and phase, and thereby it draws equal currents in the three phases. See here, one presupposition has been there that system voltages are balanced. That means when you have a generator, you have identical coils and they generate equal EMF displaced in 120 degrees without any problem. So that has been assumed. As you can see in this diagram, for both delta and star, you will find that the magnitude of currents will be same in all the three phases, hence in all the three lines. As you recall, in the case of a delta, line currents are more than the phase currents, and in case of star, line voltages are more than the phase voltages, whereas line voltages are equal to phase voltages in a delta, and the line currents are equal to phase currents in case of a star. So these are some of the issues, fundamentals which we are trying to recall, which we have learnt in basic electrical engineering courses. Now, as I said, loads could be balanced, loads may be unbalanced. In fact, I had already made a statement that loads are generally unbalanced. Having already said what is a balanced load, we know what it is to be an unbalanced load. Impedance nature is not same in the three phases. Though while designing an electrical system, designer takes care to see that all the three phases are loaded equally. Supposing a room is getting a three-phase supply and it's got 3 rows of seats, what designer would do is lamps pertaining to one row of seats are loaded on R, the other row on Y, third row on B. That is how one does. But while using, it's not necessary. There may be a situation when one row of seats are not occupied and thereby that phase is not loaded at all, and that's the situation. And another interesting thing is, although by design one can have a balanced system, but when the power is going to be used or power is going to be drawn, it depends on the user, and I as a designer or generator have no control over the user. So coming back to the discussion on unbalanced thing, as you can see, for both for delta and star, you find that the magnitudes of these currents are distinctly different. See, in case of a balanced system, because of the nature being same, the currents are going to be same. Now this diagram, you can see one thing, I have not put same impedance Z1, Z in all the three phases of delta or star. They are marked as Z1, Z2, Z3. That means each phase has a different impedance. Maybe resistance is different, maybe reactance is different, maybe both are different. In either case, it becomes unbalanced. This is how one could see that the loads could be balanced or unbalanced. Now the question arises, what do we understand by distribution? Distribution is the ultimate way of delivering electrical energy to the users. And at what voltage do you do? Now if you recall, I have already said we use the voltage at 400 volts 3 phase all around. All our appliances are operating at 400 volts, but is the distribution done at 400 volts? That depends on some factors which we will address. As seen, a sparsely populated short distance distribution is at 400 volts. Why? Again the reason is same. If the length is longer, the resistance is going to be higher, the losses are going to be higher. That is what has to be kept in mind. And on the other hand, I did mention the distribution levels could be anywhere from 11, 33 and 66. As said, densely populated or vast areas, distribution is at 11 or 33 kV. Now when you are distributing, there are two alternatives that are available to us, and one of these is through underground cables, or the other is overhead lines. Again, the option depends on the requirements, like where the population is dense, the number of buildings are large, it may not be possible to get space to erect overhead lines, and there one goes in for underground cables. On the other hand, where the space is available, you go for overhead lines. Going by this, you will find that urban localities are invariably serviced by UG cables, whereas rural settings where a lot of space is available, they are serviced by overhead lines. This is to be borne in mind. So commonly the cables means cable has a conductor and an insulation, and commonly employed cables are XLPE or cross-linked polyethylene cables, PILC, or paper insulated lead covered cables. These could be single core at higher voltages or multi-core at lower voltages. So now, having said so much, if it is a single small building, you might find that the servicing is at single phase AC 220 volts 50 hertz, whereas a very large building serviced by 3 phase AC loads at 400 volts 50 hertz. If there is a very large building, it's quite possible that the supply could be at 11 kV to the building and it is redistributed at 400 volts. This is to be kept in mind. Now, to summarize the lecture, we see that the professionally illumination engineering profession is distinctly different from other professions in the sense it needs inputs from physiology, psychology and exact sciences of mathematics, chemistry, physics, keeping in mind the economics aspects because optimal utilization of resources and the aesthetic sense of an architect is necessary to achieve the end goal of making a good illuminating system, which is a must for acquiring the information. As already told, 80% of the information acquired is through eyes and they depend on the light, and we are trying to make the light as close to the natural light as possible. As can be seen, good lighting is very much necessary. Our eyes can see clearly and pleasantly perceive the things if there is good lighting. Artificial lighting can use some form of physical phenomena. After all, we said there are artificial lights which try to bring it close to the natural light, at the same time economize the resources and use electrical energy. But there is some form of a physical phenomena which we will consider in a subsequent lecture on radiation. It could be by way of incandescence, electroluminescence, fluorescence or phosphorescence. All of us are aware of incandescent lamps we have been using for a very long time, and even fluorescent lamps which have become abundantly available, and other discharge vapor lamps which are used in the streets. And so that is the one way, and as already told, all lighting sources invariably employ electrical energy, and as told already, the electric current sources, they are either DC or AC. In fact, historically the first transmission system was direct current, but the ease of stepping up, stepping down with the help of a transformer has brought in AC into prominence. It could be single phase or three phase. However, this energy is generated predominantly using hydro or thermal. This picture shows a complete power system which comprises of a generator, a transmission system which could be at 132, 220 or 400 kV, 400 kV being the highest in the country at this point of time, and a distribution line which may be at 66, 33 or 11 kV and further step down and supplied at 400 volts three phase. And as already told, load is invariably unbalanced for a practical three phase system. So we end up this lecture with a certain questions to be addressed, and these questions will be answered in a subsequent lesson. Number 1, why do we go for transmission of power at higher voltages? 2, what do you mean by good lighting? 3, what are two ways through which power can be distributed? 4, how do you decide the distribution voltage level for a particular area? 5, what do you mean by 400 volts three phase in the Indian system? When is the load balanced? When do you go for single phase or three phase supply? Thank you. Thank you.